Pascal's identity 2.1e. Okay. So first theorem is Pascal's identity, which states that if collection ei greater than or equal to 1 means collection e1, e2, etc. be an orthonormal system. Orthonormal system means inner product of ei comma ej is equal to delta ij. That is, if I equal to j, inner product of ei is 1, otherwise 0. Then this collection ei is a basis in H if and only if norm x square is equal to sigma 1 to infinity, that is sigma I greater than or equal to 1, modulus of inner product x ei the whole square. Okay. So first suppose that collection ei 1 to infinity is a basis in H. So any element of H can be expressed as the linear scalar multiple of a linear combination of this ei. Let this scalars be inner product of x ei. That is, x can be expressed as x is equal to sigma I equal to 1 to infinity inner product of x ei. So this is arbitrary x, that is every x can be written as a form like this. Now we have to show that if it is a basis, then norm x square is equal to this one. So we start with the norm x square. Norm x square is norm of this sigma. Sigma equal to, I greater than or equal to 1 inner product of x ei the whole square. So again this by corollary 2.1.3, or either you can write this as sigma 1 to infinity inner product of x ei comma sigma inner product of x ei, and by simplifying this you will get this, that is, we know that norm x square is nothing but inner product of x. Similarly, by simplifying this we will get norm x square is equal to sigma 1 to infinity modulus of x ei the whole square. So we prove the first part. Okay. Now to prove the converse, we have to assume this one, and we have to show that this collection ei is is a basis already given, that is an orthonormal system. We have to show that if such an equality exists, then this collection ei is a basis. Now suppose that collection norm x square is equal to norm of sigma equal to 1 to infinity inner product x ei square. Okay. Now we started with this one, x norm of x minus sigma 1 to n inner product x ei the whole square, which is equal to norm x square minus sigma 1 to n modulus of inner product x ei whole square. And since norm x square is this sigma, their difference converges to 0 as n tends to infinity. Hence here this is finite terms, and we assumed that norm x square is the sum of infinite terms. So as n tends to infinity, this n tends to infinity, hence this infinite sum will be equal to norm x square. Therefore x is equal to sigma 1 to infinity inner product of x ei, that is, it is the linear combination of ei's, that is collection ei is a basis. Okay. And now let us prove this one, that is how comes this equation from the second equation. So again we started with this one, norm of x minus inner sigma 1 to n inner product of x ei the whole square. Since norm x square is equal to inner product of x comma x, we can write like this. And in first argument position, this can by the definition of inner product, we can write like this: inner product of xx minus inner product plus or minus inner product of sigma 1 to n inner product of x ei minus inner product of sigma 1 to n inner product of x ei ix, and next term. Okay. Now, inner product of xx is norm x square. And if we are considering the second term, there is a scalar in the second argument's position, and if we are taking it from that second argument position, it will comes as inner product of xei conjugate into sigma xei. Similarly, we can simplify other terms also, and we can prove that it is same as norm x square minus sigma 1 to n modulus of inner product xei whole square. Okay, now this is a theorem. Any two separable infinite dimensional Hilbert space H1 and H2 are isometrically equivalent, which means there is a linear isomorphism between H1 and H2 such that norm Tx is equal to norm x. Moreover, the inner product, that is inner product H2 of dx dy is equal to inner product h1 over h1 of x comma y. Okay, so we are proving that we are considering H is any infinite dimensional Hilbert space and H2 is L2, since L2 is a separable infinite dimensional Hilbert space. We are going to prove a connection between capital H and L2. Okay, so it is enough to build such a T for a given H in the place of H1 and L2 in the place of H2. H is a separable infinite dimensional Hilbert space, means there exists a orthonormal basis by corollary 2.1.11. For a very separable infinite dimensional Hilbert space, there exists a orthonormal basis. Let it be collection Fi. And for every x belongs to H, x can be expressed as the linear combination of this collection Fi. Therefore, norm x square is equal to sigma 1 to infinity modulus of x Fi whole square. Either you can prove this by corollary 2.1.3 or simply by using the fact that norm x square is inner product of xx, and by substituting the value of x here, you will easily get this result. Now, let collection ei be the natural basis of L2. Now this is our x. So Tx means T of sigma, that is this sigma inner product of x Fi is a scalar which you can take it outside, and T of Fi is equal to ei. We know that if it is a mapping, then it maps basis of H2 basis of L2, that is T of Fi can be considered as TEI. This element belongs to L2, that is Tx is equal to, this is scalar linear combinations of EIs, and EIs are the basis of L2, therefore Tx belongs to L2. Hence we prove that T is a mapping from H to L2. Okay. Now we have to show that norm Tx is equal to norm x. So we started with norm Tx the whole square and replaced the value of Tx here, norm of sigma 1 to infinity inner product of x Fi ei the whole square, which is nothing but inner product of sigma inner product x Fi ei comma sigma inner product x Fi ei, and there is an inner product of x Fi in the first argument position, and there is also such term in the second argument position. So if we are taking from first argument position, it will come as inner product of x Fi. From second argument position, inner product of x Fi conjugate, and there is ei. Again, one term is the inner product of ei. Now inner product of ei is equal to 1, since collection ei is a orthonormal basis, and inner product of x Fi conjugate is so this is of the form zz bar, which is equal to modulus of z square. So sigma 1 to infinity modulus of inner product x Fi the whole square, which is equal to norm x square. So taking square root on both sides, we will get norm of Tx is equal to norm x. Now clearly T is on to, that is To show that T from H to L2 is on to, we should find some element in H for every y belongs to L2. Okay, so if y belongs to L2, be Tx such that y is equal to sigma 1 to infinity inner product of x fi ei, and if we can choose in such a way that T fi is equal to ei, we can find a x as sigma 1 to infinity x fi into fi belongs to capital H as T of x equal to y. Therefore, clearly by the definition of T itself, Tx and y, we can prove that is onto. Now we have to show that this inner product of Tx dy in the space L2 is same as inner product of xy in the space H. So we started with inner product of Tx dy and substituted for Tx and dy. Here inner product of x fy is in the first argument position. We can take it outside, and inner product of y fy in the second argument position, we can take it outside as y fi conjugate, and simplifying we will get this equation what, that is sigma inner product of x fi into inner product of fi y. Similarly, inner product of xy in the space H can be written as inner product of replace x by sigma inner product of x fi and replace y by sigma inner product of y fi and simplifying we will get equation 2, and from equation 1 and 2 we can easily prove that inner product of dx dy in the space L2 is nothing but inner product of xy in the space H, hence the proof. Now we are defining a space L2 of I2 where I is a closed interval AB as the completion of the space of square integrable continuous function of two variables with the norm of f of t comma tau is equal to root of double integral over I modulus of f of t comma tau the whole square dt d tau.